So this is how our galaxy should look to a observer viewing it from above the disk. We know that these spiral arms exist because they are outlined by associations and open clusters of very hot and luminous stars. They are blue, and we learned that such stars outline the arms in other spiral galaxies. Also, we can locate the gas and dust in our Milky Way galaxy, and it is also distributed along these spiral arms. So the question is, what are they? Well, they are the waves of compression of the material in the disk of the Milky Way, and they move around more slowly than the stars that revolve around the galactic center. Okay, so basically what is happening is, if this is one spiral arm of the Milky Way, it's rotating more slowly around the galactic center than the individual stars or clouds of gas and dust. So say we have here a cloud of gas and dust that moves more quickly than the spiral arm itself. So eventually it will catch up with the spiral arm, and when that happens, as it starts entering the region of the arm, it will get compressed and will trigger the star formation. So here is the same cloud that is entering the spiral arm, but at the same time it is triggering the star formation. Okay, so we will have different types of stars depending on the masses of the clumps. Some are going to be hot, luminous stars. Some are going to be like our sun, garden variety yellow stars, yellow-white stars. And some are going to be smaller mass and therefore reddish stars. So what kind of star is formed depends on the mass of the clump that contracts and eventually produces the star. Now, these hot luminous stars do not live long, and essentially they spend their entire life within the region of the arm. On the other hand, medium mass stars like our sun, or even smaller mass stars, they live much longer. The lifetime of a star like our sun is about 10 billion years, so they will survive this trip through the spiral arm and eventually come out moving along, right? So some of them are stars like sun, some of them are smaller mass stars. Okay, so lower mass stars. So you can say, well, okay, so it's crowded. How come that the stars don't run into each other? In particular, for instance, our sun was formed in an event like this, some 4.6 billion years ago, and as we calculated, it has made 20 round trips around galactic center since then. So you can ask the question, okay, so once it passes again through the spiral arm, how come it doesn't run into other stars there? Because if that region is more crowded. Well, the point is that the average star-star distance is much, much bigger than the diameter of any given star. Recall that the stars closest to us are at about 4.3 light years away, so it's typically a few light years, which is 10 million times larger than the diameter of individual stars. Therefore, the probability of two stars colliding is exceedingly small, near zero. So it would be just like, say, we had two flies in this theater here, right? Moving around, because the space available to them is so much larger than their size, the odds of two of them running into each other is very small. As we say in physics, the collision cross-section is very, very small. Okay? So the sun and other stars that have been formed before, those that live long and make several trips around galactic center, in spite of the fact that they are passing through other spiral arms, the odds of them running into another star are virtually zero.